So you might notice that I am harping a bit about how we treat the infinity sign, a bit more than my usual carefree mathematical manner. We got to be really careful here because, again, plus and minus infinity are not real numbers. They are useful, but a lot of the kinds of algebra that we would like to do, well, some of it works for plus and minus infinity, but a lot of it actually doesn't. And we can get into some wrong answers very easily if we're not careful about it. So for example, let's take this limit, x is approaching 1 from the right. There's my plus sign to denote from the right. The function I'm looking at is x plus 1 divided by quantity x minus 1. All right, well, I know that that x, this x right here, that's just going to 1. Easy, easy peasy. But this x on the denominator, that's also going to 1, which means that denominator is going to 0. It's going to 0 from the right, so that's going to be positive, which tells me that this rational function here, as x tends to 1, this is going to go to positive infinity. Well, the first piece is going to 1. The second piece is growing without bound. Well, then the whole thing together has to be growing without bound. That's kind of a lot to chew on. That's a fairly abstract idea. So we use the shorthand idea. We use a placeholder to say, well, this piece is going to 1. This piece is going to infinity. 1 plus infinity is infinity. Hey, that's intuitive, right? That helps us understand. But this kind of algebra is not the same as algebra where I'm saying 1 plus 2 equals 3. I got to be careful about stuff. I got to be really careful about, say, even subtraction. If I'm doing this idea of breaking a limit down into pieces, both pieces of the limit go to infinity. What if it's an infinity minus infinity situation? I don't actually have a hard and fast rule for it. It's going to be context dependent. So that's the reason why I'm being a little bit, more stern and more strict with this language. It's so that we don't end up accidentally getting a wrong answer.